Oh, this video will discuss the masses of stars and the mass-luminosity relationship, especially that's the key element. But for the stars on the main sequence, so these are stars that have been recently born, quote-unquote recently. Um, these are not stars in the latter stages of their lives. These are stars that are fusing hydrogen to helium in the core of the star. So on the main sequence, fusing hydrogen to helium in the core of the star. So astronomers, we've found out, have the ability to make some measurements about stars. One measurement is the luminosity of the star. This is the true energy output. And the way this can be measured is to measure the apparent energy output, how much energy is received at the Earth, and then do a calculation that corrects this based on distance. With the parallax numbers being known, and there are some other methods of determining distance, not quite as accurately as the parallax, but with parallax we get a distance to the star. We on the Earth with telescopes measure the apparent brightness of the star, and then we can calculate the absolute brightness of the star, the absolute magnitude, the luminosity, based on the measurement of apparent luminosity, how bright it appears to us, the star appears to us, and the distance to the star. We can correct for distance and calculate the true energy output of the star. So luminosity is one thing. And then the spectroscopic binary stars provide the mass numbers for stars. So we can get the value of how much material is in the star. When this is graphed, we find that there's a relationship, a strong connection between the mass of a star and the luminosity of the star. And this doesn't show the full relationship here, but there is a correlation, a trend. So is that just a happenstance, or is there some reason? And the correlation is that the luminosity is proportional nearly to mass raised to the 3.5 power. So it's not m cubed, it's not m to the fourth, it's in between. And we'll do some approximations, so you won't have to use a calculator to do the easy cases. So one easy case would be, suppose the mass is 3 times the sun. If the luminosity is proportional to mass cubed, then we'd have 3 times 3 times 3. For the calculation, that's 27, and we get 27 times the luminosity of the sun. If this was luminosity proportional mass to the 4th power, then we'd have 3 times 3 times 3 times 3. That's 81, 9 squared, and gives us a number bigger than this. So the 3.5 power, it gives us a number in between. I've worked it out with a calculator, and the luminosity would be about 47 times the luminosity of the sun. So that's the behavior. On the main sequence, the star has to be on the main sequence to follow this rule, this relationship. There's a connection between luminosity and mass. So what causes this behavior? Why is it that the more massive stars are more luminous? I'd like you to take 30 seconds or so, pause the video, and see if you can come up with an explanation. Why are the more luminous stars those that are more massive? Why is it that mass has this big effect on luminosity? Well, the mass of the star determines the temperature at the core. We have this mass of the star pressing down on the core material, causing it to, if it's a more massive star, to press in more on the core, make the density of the core higher, and make the temperature of the core higher. The temperature of the core gives us a pressure. So if we have more mass that needs to be supported, our core is going to have a higher pressure. If our star is in equilibrium, and the stars on the main sequence are basically in equilibrium, very slow change is taking place. So we have equilibrium, more mass requires more internal pressure to support those outer layers. And that internal pressure comes from increased temperature and somewhat increased density, but the temperature is key, because the temperature adjusts the rate of fusion. The ability of one proton to get near to another proton is greatly influenced by the temperature of the protons. So If we have higher temperature, that means more speed for the particles, and more of them get to this close condition where the strong nuclear force can take over and fuse the two protons into a helium. And that's very simplified, but that's basically what happens here. Higher temperature, faster particles get closer, strong nuclear force is going to get more of them. In addition, having the higher density for the core is an advantage for producing energy, because if we have a more dense situation, it's more likely that two protons are going to collide at in such a way that they get close to each other, or more of a head-on collision than just a glancing collision. So the rate of fusion goes up. The rate of fusion is very dependent on the temperature. Temperature is a very crucial parameter, a number that is used to greatly influence the rate of fusion. So more mass, the core has to supply more pressure to hold up the outer layers. The core is going to be compressed a little bit, more dense, but especially the core is going to have a higher temperature when the equilibrium is reached to balance the outer layers, the inward weight, balanced with the force outward from the internal pressure. So energy goes up, mass to the 3.5 power. In terms of approximately what is the lowest mass star and what's the highest mass star, around 1/10 of the sun's mass is the place where, if we're below that, then there's not as much mass pressing on the core. The core is not compressed as much. The core temperature is not as high. And it gets to the point in these low mass stars where the temperature is too small for one proton to fuse with another proton. Now there is an isotope of hydrogen called deuterium that has a proton and a neutron, and that has more inertia, more momentum, as the particles are moving around, and consequently, maybe I'll just say more inertia. It's easier for these particles to get close to each other. So I'm going to take a little break and let you think about that. So I hope you're in agreement there that if the mass is too low, we don't compress the core enough, the core doesn't get to high enough density, high enough temperature, because high temperature is not needed to create the pressure needed to balance a small mass of outer layers. So there are some stars right on the boundary of this, a little bit smaller perhaps, that the deuterium isotope of hydrogen can fuse together, but there's not as much deuterium as normal hydrogen that just has a proton in the nucleus and no neutron. So we get a short lifespan for these stars. Are smaller, cooler, and shorter life. On the high end, if the mass is very great, again, we're pressing in here, collapsing, not totally collapsing the core, but pressing in, making the core more dense. The temperature of the core has to get to a higher value to support the outer layers with this internal pressure. So we get a higher temperature in the core. This higher temperature makes the rate of fusion tremendously much higher. That's why it's mass to the 3.5 power. This increase in mass has a great increase on temperature. This great increase in temperature causes an even greater increase in the rate of fusion. That the rate of fusion depends critically on the temperature. As the temperature goes up, we get a more abundant rate of fusion going on. More of the protons are able to get close to each other. And then having a denser core, we get more collisions, more fusions happening. So this ends up producing so much energy for 150 times the mass of the sun that light is able to push material away from the star. Light does cause things to kind of bounce back. Not much and not really measurably on the Earth, but in these stars there's so much light that it's able to push away material, and the star stops collecting mass. The mass that would have fallen down to become part of the star, that gets blown away, pushed away, I should say, by the light energy that this massive star is emitting. So, questions. You ought to write down some questions. I have a question for you. What's the difference between a star and a planet? What's the difference between a star and a planet? Stars create their own light. They have fusion going on in the core that creates energy. Planets reflect starlight. Planets reflect starlight. There are some cases where planets in our solar system emit more radiation than they receive from the sun, but they do not have nuclear reactions going on in their cores. They're contracting slowly and releasing energy, and they give off this energy in the infrared. It's not in the visible wavelength, so we don't have multiple stars in our solar system. We just have one star. There's only one place where hydrogen is fusing to helium. That's at the core of the sun. So stars have fusion of hydrogen to helium, or they have fusion of something. They have nuclear reactions. For stars on the main sequence, hydrogen to helium. Planets do not have nuclear reactions going on in their cores. So keep reading on that, write down some questions, and ask your instructor.